All right, we're gonna now work on another hypothesis test, and we're gonna do hypothesis tests on a population variance or standard deviation. Okay, there are a variety of reasons you might want to do a test on a variance or standard deviation. Some common ones, just to kind of motivate this briefly, frequently in product manufacturing, if you are manufacturing a specific device or a component or something, you could even think about like some hardware, maybe like a screw or something like that. There's some tolerance limits, right? If you really measure your length closely, very closely to minute detail, there's gonna be some wiggle room, right? And what's considered acceptable, you want to have a low standard deviation there, or a low variance in your production, so that, if I'm going to buy a 1-inch screw, that they're all basically 1 inch plus or minus, 0.001, or some limit that's acceptable to the manufacturer there. All right. And so, claiming that your production process actually produces things within this tolerance limit majority of the time, that's a scientific claim that you're making, and you can do a test on the variance, or that the standard deviation is, plus or minus 0.001. That's one common thing. Quite frankly, in just terms of applying this to statistics, is a lot of hypothesis tests or a lot of just other inferences rely on us using information about the population variance or standard deviation. And so we have to make assumptions, right? If we're doing hypothesis tests on the mean, sometimes we are assuming that the population, we know the population standard deviation, right? Other tests comparing two samples and things like, are two population means actually different, require us to make assumptions about the variance in those test statistics, right? And so when we are making those assumptions, someone could do preliminary analysis, right, to verify, if we're going to assume the population variances are the same or different, we could do a test on the variances beforehand to make sure that we're not violating any of those assumptions, okay? But I don't want to spend much more time than that talking about some of the reasons. The hypothesis test procedure itself is more or less going to be the same, but when we're talking about a variance here, remember, we're going to have a different test statistic. So I want us to remember, this is a while back, but we're talking about a different test statistic. We're going to be talking about using the Chi-Square statistic, right? Chi-squared, our Chi-square value, is calculated as n-1 times the sample variance over the assumed population sample standard deviation. And so sigma squared, I'm going to write this as sigma squared sub 0, writing out a sigma squared sub 0 in regards to the hypothesis test, because sigma squared sub 0 is going to be the null hypothesized value. This will be the null or assumed value, the null or hypothesized value of the population variance sigma squared. And we have this test statistic, and the test procedure is more or less the same as it is if we're, testing on a mean or something like that. I do want to mention, I would have regrets if I just didn't mention this, just to be aware of, is that in practice, when we're doing a chi-square test here, it really relies, it's not very robust to non-normality, which means that this heavily relies on the underlying data being pretty close to normally distributed. A chi-square test, chi-squared test, relies heavily on normality of the underlying data. Heavily on normality of the underlying data. Other tests don't, with a large sample size, other tests are not as affected as much by non-normality of the data. The t-test is a good example of something that's pretty robust if you have a decent sample size. But a chi-square, it is heavily reliable on the data being normal. And we're not going to really deal with anything that's not normal because we're just trying to get the feel for hypothesis testing. But I will mention that there are ways to fix this. And if you go on to look at further data analysis or statistics, a common way to deal with non-normal data is to transform it so it is normal. So one way to fix non-normality is to transform the data. A common thing that can happen is if your data only has positive values, and maybe it's heavily skewed toward the right. So maybe it's something like, house prices in a given locality. House prices are never going to be negative, and you might have a couple really, really nice $1 million houses. So that distribution, that tail to the right is going to go really far. That's not normal, but a logarithm transformation would help make that data look much more normal. Okay. That's neither here nor there, really. It relies heavily on normality of the underlying data. Again, just in full disclosure, right? That is something that we would consider. Now, the hypothesis testing procedure generally remains the same. The hypothesis testing procedure generally remains the same. And this is, mostly true for any hypothesis test. You're going to find and identify your null and alternative hypotheses. You're going to find your test statistics. You have a level of significance, and you're going to be, you could look at a p-value or a critical region of some sorts to reject or fail to reject your null hypothesis. So you'll see that this process is going to be very similar. It's just instead we're working with a chi-square statistic, and then we're going to be looking at a chi-square distribution to talk about our p-values and probabilities. Let's dive into an example. A manufacturer of car batteries claims that the life of their cheapest battery is approximately normal. With standard deviation equal to 0.9 years. Standard deviation equal to 0.9 years. We have a random sample of 10 batteries. A random sample of 10 batteries yields a sample standard deviation S of 1.2. We take a random sample of 10 batteries, and the standard deviation there's 1.2, which is greater than 0.9, So that might lead you to think that the standard deviation is underreported there. So let's go ahead and test the alternative hypothesis that sigma is greater than 0.9 at a 0.05 significance level. All right. So we're going to go ahead and set up our hypothesis test, our null hypothesis. Notice this is standard deviation. You got to be careful here because the chi-square statistic is for the variance. So this is not on the standard deviation, so we need to square our standard deviation to get to the variance. So the null hypothesis would be that the population variance is 0.9 squared, or 0.81. versus the alternative hypothesis, which would be that the variance is greater than 0.81, 0.9 squared being the 0.81 there. All right, so that is our tests. That's our alternative. Notice that this is a one-sided test. This is a one-sided test. One-sided test with a significance level of 5% with alpha equal to 5%. Alpha equal to 5%. Okay, so this means then what will we can define our rejection region here. We will reject the null hypothesis, right? If our test statistic is more extreme than this 5% cutoff, we would reject the null hypothesis if we get a chi-square value that is bigger than, right, in favor of the alternative, more extreme, bigger than the chi-square value that's going to leave us with 5% area to the right, 5% area to the right. So let's go ahead and take a look at that in the table. Remember, the chi-square statistic requires us to use a degrees of freedom. That's n-1 degrees of freedom. So we had a sample of 10 batteries. So we have 10 minus 1, 9 degrees of freedom. We should go to the table and look at a chi-square value with 9 degrees of freedom. That's going to give us 5% of the area to the right. Let's tab over to the chi-square table real quick and take a look at that. And here we are. This is the t-distribution. So let's go to chi-square. Remember, this gives you the area to the right of the curve here in the chi-square and the t-tables. So we want a 5% alpha, area to the right, 9 degrees of freedom. Looks at the table here, it should be 6.919, I believe, is the value I want. 6.919 right there. Looks good. Sorry, I said 6, I misspoke. That's 16 in the table, right? It was 16.919. 16.919. And if needed, right, we can always think about drawing a picture here. It's never really that bad of an idea to draw a picture. Chi-square distribution looks something like this. So here is our 16.919. 16.919. There is a 5% area right there to the curve, okay? This is also called the critical region, I should mention. This is also called the critical region. Your rejection region, also called the critical region. If we get a chi-square statistic anywhere in our critical region, we're going to go ahead and reject that null hypothesis. So 16.919, that's our cutoff. What is our test statistic then? What's our chi-square statistic test? Statistic. Remember, this is n-1 times the sample variance over the assumed variance under the null hypothesis. So we have n times the sample standard deviation was 1.2. So that's going to be 1.2 squared divided by the sigma squared under the null hypothesis, which is 0.81. And so we run that through a calculator, and it's about an even 16.0. 16.0. 16.0. All right. So now we can make our decision, our conclusion. Is 16.0 in our rejection region? Well, no, our chi-square cutoff value there started at 16.919 and greater, since 16.0 is not in the critical region. We fail to reject the null hypothesis. There is not overwhelming evidence. There's not overwhelming evidence at a 5% significance level that the standard deviation is not 0.9 or that the sample or the variance is not 0.81. That is, we do not have enough evidence to reject that hypothesis based on our sample. Okay. I will mention, if you want to think about this in terms of p-values, right? Remember, a p-value would be getting a more extreme test statistic than what we have. If we look at our p-value, so if this is 16.919, 16 would be something like right there. Our p-value is going to have a larger area, and we could look that up approximately. It's not exactly in the table, but I'll just mention for our own curiosity. The p-value here is about 7%. The p-value is about 7%, which is bigger than our 5% cutoff, which is our type 1, alpha, right? Our significance level, alpha. Okay. Either way, critical region p-values, right? At a 5% significance level, we would fail to reject the null hypothesis. It's close, but the ending conclusion is we fail to reject at a 5% significance level.